lesson 9, which covers boiling points. But before we get into that, we are going to do a little bit of review from yesterday's lesson. Now, the first question says, explain why water has hydrogen bonding and hydrogen cyanide does not. So for hydrogen bonding to take place, what needs to happen? Who knows? Hands up. Jen. Right. So hydrogen needs to be directly connected to one of these three elements. Okay? Water, what shape does water form, first of all? Just to review that. Bends. Hydrogen cyanide, what shape does that one form? Linear. Good. So notice how hydrogen is directly connected to that oxygen there. It's part of that bond group. Here, there is no connection between the nitrogen and the hydrogen. Therefore, there is no hydrogen bonding there. So now between these two, who has a stronger bond? Water. Good. Okay. Tell me if I'm wrong. But for this one, we should have 3, 2, 1, 3. Do we agree? Yes? Okay, let's get into today's lesson then. Okay. The learning goals for today's lesson. We're going to understand the effects on boiling points, so the correlation between intermolecular forces and boiling points. We're going to rank molecules based on their boiling point, and then we're going to create, interpret graphs. Okay? So let's get into that. Remember that IMFs stand for intermolecular forces. Okay, so we're going to look at the intermolecular forces effect on boiling point. The stronger the IMFs, or the intermolecular forces, the higher the boiling point will be. For example, if we were to compare hydrogen cyanide and H2O, hydrogen cyanide would have how many intermolecular forces? How many would it have? 2. Has London forces, because everything with electrons has London forces. What gives it dipole-dipole forces? If it's polar. Right, so this one has 2. Water has how many? 3. It's a polar molecule with hydrogen bonding. Therefore, it has 3 intermolecular forces. Now, comparing these two, which one would have a higher boiling point? Water. Right. So H2O would have a higher boiling point because it has more intermolecular forces. Oh, that's a horrible M. Fix that. Yeah, amazing. So I want you to take 30 seconds, Google what the boiling point of HCN is, and Google what the boiling point, well, hopefully we know what the boiling point of water. Wait. Hazel, give me the boiling point of hydrogen cyanide. 25.6 degrees Celsius. Water, what is the boiling point of that? You should all know it. 100. Okay, so this makes sense with the theory. Water boils at 100 degrees Celsius. We know that. It is much higher than hydrogen cyanide, which boils at 25.6 degrees. This one has 3 intermolecular forces. This one has 2. The more intermolecular forces, the stronger those bonds are, the harder they are to break. Now, what if we get into this situation where they have the same number of intermolecular forces? How are we going to decide who is going to have a higher boiling point? So when comparing compounds with similar intermolecular forces, the total number of electrons would help determine boiling point. Now, I want us to be very careful. We have been counting valence electrons, okay, in the past since we have started this unit. When we are looking at boiling points, we are going to count the total number of electrons, not just valence, all of them. For example, if we have bromine and fluorine, both of them only have London dispersion forces. London dispersion forces, okay? We need to compare the total number of electrons. Again, emphasis on the total there. Okay, who can tell me how many total electrons bromine has? Yes, so there are 2 atoms of bromine. They each have 35 electrons each for a total of 70. How many does fluorine have? 18, good. Therefore, bromine would have a higher boiling point. And the reason being is because because it is heavier. Okay, so think about it like this. As a molecule gets heavier, it requires more energy, okay? And energy in science means heat, okay? So the more energy that is required, a higher temperature is needed, okay? So the heavier the compound gets, the more energy is needed, the higher the boiling point, okay? Think about pushing something light up a hill, requires less energy. Think about pushing something heavy up a hill, requires a lot more energy, okay? Before we get into graphs, I want to go over kind of what boiling means. So remember this from yesterday, how we have 2 water molecules that form a positive and negative pole, okay? So there is an intramolecular bond there. As the temperature is cooler, this intramolecular connection is going to be stronger. As the temperature gets higher and higher and we approach boiling point, this bond here is going to break. We become in gas form when compounds are separated from each other. So they're no longer connected by this intermolecular force, okay? So once the compounds are separated, they turn into gas form, they have reached boiling point, okay? So that's what it means for something to be boiled. Here we have a graph that is comparing a bunch of different compounds and their boiling points. So on the y-axis here, I have boiling points listed. And on the x-axis here, we show the total number of electrons in the compound. So now looking at this graph, we notice that hydrogen, hydrofluoric acid, and ammonia have significantly high boiling points. Why is that? Yes. They have the strongest IMF. Which one is that? Hydrogen bonding. They have hydrogen bonding. Which is the strongest IMF. The stronger a bond gets, the harder it is to break, the more energy it requires, raising the boiling point. What do you notice happens when the boiling point of the molecule gets bigger? Wait, what do you notice happens to boiling point as the molecule gets bigger or the molecule gets heavier? So let's look at this green line here. It starts off and it goes up. So what do we see? What is happening to boiling point. It's increasing. So as molecule gets bigger, boiling point increases.